Tonight, we're going to look at a number that almost everyone gets wrong: the distance between solar systems. Most people picture a handful of light years, something large but manageable, a gap that better rockets could eventually close. The real number is far worse than that. For the vast majority of stars in the galaxy, the nearest solar system isn't a few light years away. It's dozens, sometimes hundreds, separated by a darkness so complete that reaching it isn't just difficult, it's close to physically impossible. By the end of tonight, you're going to understand exactly how far apart solar systems really are, what actually fills the space between them, and why this distance may be the hardest barrier the universe has ever built. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something familiar. You live on a planet. That planet orbits a star. That star, our Sun, sits at the center of a system of 8 planets, dozens of moons, hundreds of thousands of asteroids, billions of icy bodies stretching out to the very edge of the Sun's gravitational reach. All of that, every planet, every moon, every rock and comet and speck of dust that calls our Sun its anchor, fits inside a sphere roughly 3 light years across at its absolute outermost boundary, 3 light years from edge to edge. That is our home. It is enormous in everyday terms. If you drove at highway speed without stopping, you would need about 6,000 years to cross the distance from Earth to Pluto. That is just reaching the outer edge of our planetary system. Still well inside the solar system. Our solar system is not a point. It is a vast, complex structure that took billions of years to form, shaped by the competing gravities of 8 planets and hundreds of thousands of smaller bodies, all orbiting a single star. The planets alone span distances from Mercury's orbit at about 36 million miles from the Sun to Neptune's orbit at roughly 2.8 billion miles. That is a spread of nearly 3 billion miles just between the innermost and outermost planets. 3 billion miles. The Apollo astronauts took 3 days to travel 250,000 miles to the Moon. At that same speed, reaching Neptune would take over 90 years. Beyond Neptune sits the Kuiper Belt, a disk of icy objects extending out to about 4.7 billion miles from the Sun. Beyond the Kuiper Belt, the Oort cloud, a vast, spherical shell of frozen material. Comets in waiting, extending perhaps 1/4 of the way to the next star, maybe even halfway. The full reach of our solar system, edge to edge, is measured in light years. And still, in the context of what we are about to discuss, it might as well be a grain of sand, because the nearest star to our Sun is Proxima Centauri, part of a triple star system called Alpha Centauri. And it sits 4.24 light years away, not from the edge of our solar system, from the Sun itself. 4.24 light years. A light year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In 1 year, it covers about 5.9 trillion miles. 4.24 light years is roughly 25 trillion miles. That is the distance to the nearest solar system, the next one over. And it is not the only one separated from us by that kind of gulf. Every star in the night sky is separated from every other star by distances in that same order of magnitude. Trillions of miles, not billions, trillions. And we are here, on Earth, with no meaningful ability to cross it. This is the situation. It sounds abstract. it is not. To understand what this gap actually means, you have to understand where our solar system ends and where interstellar space begins. The boundary is not sharp. There is no line you can point to where the sun's influence stops overnight. But there is a region, called the heliopause, where the stream of charged particles flowing outward from the sun, called the solar wind, finally gives way to the broader interstellar medium. The solar wind is a constant outflow of electrons, protons, and alpha particles blowing off the sun's outer atmosphere at hundreds of miles per second in all directions. It has been blowing continuously since the sun ignited, roughly 4.5 billion years ago. It extends outward, inflating a bubble of solar influence called the heliosphere. This bubble encompasses all 8 planets, the Kuiper belt, and extends many billions of miles beyond. At the heliopause, the outward pressure of the solar wind finally matches the inward pressure of the interstellar medium pushing back from outside. A balance point, a boundary. Beyond that boundary, the sun no longer dominates. Out there, it is just another star, one of hundreds of billions in the Milky Way, visible as a faint point of light rather than the overwhelming presence it is from here. Voyager 1 crossed the heliopause in August of 2012. It was the first human-made object to enter interstellar space. The announcement was celebrated. Scientists who had worked on the mission since its launch in September of 1977, some of them spending their entire professional careers tracking this single spacecraft, understood what it meant. Something built by human hands had exited our solar system and entered the space between stars. That had never happened before in the history of our species. Voyager 1 is moving at about 38,000 miles per hour. It has been traveling for nearly 50 years. It is currently more than 15 billion miles from the sun. It is officially in interstellar space. And here is the number that matters. At its current speed, if Voyager 1 were aimed at Proxima Centauri, which it is not, it is heading in a completely different direction. It would take roughly 75,000 years to arrive. 75,000 years. At 38,000 miles per hour. The entire span of recorded human civilization is about 5,000 years. Writing was invented 5,000 years ago. Agriculture, maybe 10,000 years ago. We share a common ancestor with Neanderthals, somewhere in the range of 500,000 years ago. 75,000 years at the speed of our most distant spacecraft barely gets us to the front door of the nearest solar system, and Proxima Centauri is the closest one. Every other solar system in the galaxy is farther. Every single one. Beyond the heliopause, you enter a domain that has no name in ordinary life, because ordinary life has never gone there. The interstellar medium, the material that fills the space between solar systems. Most people, when they picture this space, picture nothing, a pure black void, and that is mostly accurate. But not entirely. The interstellar medium contains gas and dust, extraordinarily thin, about 1 atom per cubic centimeter on average. For comparison, the air around you right now contains roughly 25 quintillion molecules per cubic centimeter. The interstellar medium has 1 atom, 1, where you have 25 quintillion. It is the closest thing to pure emptiness the universe naturally produces. The best vacuum we can create in a laboratory on Earth, with our most sophisticated pumping equipment, still contains more particles per cubic centimeter than the space between stars. We cannot even replicate its emptiness down here. That 1 atom per cubic centimeter, spread across trillions of miles, adds up, And for a spacecraft traveling at a significant fraction of light speed, that near nothing becomes a real obstacle. Think about what happens at speed. At 10% of light speed, you are moving roughly 18,600 miles every second. In that second, you pass through a staggering volume of interstellar space. Each cubic centimeter of it contains, on average, one atom. Billions of hydrogen atoms hitting you every second. Each individual impact is nothing. A hydrogen atom has essentially no mass by everyday standards. But billions of atoms per second, accumulating over 40 years of travel, creates a measurable drag force. It slows you, not catastrophically, but enough to matter in a fuel budget that is already desperately tight. There are also magnetic fields woven through interstellar space. Thin and irregular, measured in microgauss, 100,000 times weaker than Earth's surface magnetic field. But they exist, threading through the void between stars, relics of the broader galactic magnetic field that pervades the Milky Way. Charged particles spiral along these field lines. Any spacecraft generating its own electric or magnetic fields will interact with them in ways that complicate navigation. And there is radiation, cosmic rays. High-energy particles accelerated to near-light speed by supernova explosions, neutron stars, and the jets of black holes, flying through the interstellar medium in every direction, constantly, relentlessly. They have been doing this for billions of years. In the space between solar systems, there is nothing to stop them. No stellar magnetic field of any consequence. No planetary magnetosphere, no atmosphere, no shielding, no mercy. Just open space, and those particles ripping through it at essentially light speed. The interstellar medium is not empty. It is hostile in specific ways, and every one of those specific ways has to be understood and addressed by any mission attempting to cross the gap. The radiation problem is one of the most serious constraints on human survival in the interstellar void. On Earth, we live inside several layers of protection that we never think about because we were born inside them. The outermost layer is Earth's magnetic field, the magnetosphere. Generated by the motion of liquid iron in Earth's outer core, it extends tens of thousands of miles into space. It deflects the solar wind and a significant fraction of cosmic rays, sweeping them around the planet rather than letting them hit the surface. Think of it as an invisible shield, the size of a planet, generated continuously for billions of years without any input from us. The second layer is Earth's atmosphere. Roughly 60 miles of air between you and space. When cosmic rays do penetrate the magnetosphere, they collide with atoms in the upper atmosphere, creating cascades of secondary particles that dissipate energy as they descend. By the time these particles reach ground level, most of the energy is gone. The result? On Earth's surface, you absorb roughly 2 to 3 millisieverts of radiation per year from natural sources. This is the baseline, normal, what our biology evolved alongside over millions of years. Astronauts on the International Space Station, which orbits at roughly 250 miles altitude inside the magnetosphere, lose the protection of the atmosphere but retain much of the magnetic field protection. Their annual radiation dose runs roughly 50 to 200 millisieverts per year. That is between 17 and 67 times the ground-level dose. And they are still inside Earth's magnetic bubble. A mission to Mars, leaving the magnetosphere entirely, would expose astronauts to an estimated 600 millisieverts over an 18-month round trip. That approaches levels considered career-limiting under current radiation safety guidelines for radiation workers. In interstellar space, 4 light-years from any star, the situation is meaningfully worse. No nearby star's magnetic field provides any shielding at that distance. The galactic cosmic ray flux at full interstellar intensity hits any unshielded object continuously. A crew crossing to Proxima Centauri at 10% of light speed, 42 years of travel, would face cumulative radiation doses that would be lethal without serious shielding. You can shield against it. Water is a reasonably good shielding material for cosmic rays. Hydrogen absorbs high-energy particles without producing as many dangerous secondary particles as metals do. When a high-energy cosmic ray nucleus hits aluminum or iron shielding, the collision can shatter the nucleus, creating a spray of secondary radiation. Water and polyethylene are rich in hydrogen. They absorb the energy more efficiently. A surrounding layer of water tanks, several feet thick, on all sides of the crew habitat, could meaningfully reduce radiation exposure. But water is dense and heavy. 1 cubic meter of water is 1,000 kilograms. A crew habitat, surrounded by enough water shielding to significantly reduce interstellar cosmic ray flux, might require tens of thousands of kilograms of water. Just for the shielding. That is mass you need to accelerate out of the solar system, maintain structurally intact for decades, and ideally decelerate at the destination. Adding that much shielding to a spacecraft that is already constrained by propulsion physics makes an already formidable problem dramatically worse. Magnetic shielding, generating a powerful artificial magnetic field around the spacecraft, has also been studied. The idea mimics the magnetosphere on a small scale. Superconducting coils, carrying large currents, produce a magnetic field that deflects charged cosmic ray particles around the craft. The technical challenges are serious. Superconducting coils must be maintained at temperatures near absolute zero. Generating a sufficiently strong field over a large enough volume requires substantial continuous power. Any coil failure reduces the field and exposes the crew. A repair mission from Earth is not an option when you are 2 light-years from anyone. And magnetic shielding does not stop neutral radiation. Neutrons, gamma rays, and other neutral components that magnetic fields cannot deflect still pass through freely. Physical shielding remains necessary, regardless. So, you need both. Physical shielding for neutral radiation. Magnetic shielding for charged particles. Both powered and maintained for 42 years without external support, without spare parts that can be shipped from anywhere, without engineers who can be flown in. The radiation problem is real. It is serious. It does not have a clean solution. And it is one of a stack of serious problems, each of which would be a major engineering challenge on its own. The propulsion problem is the most fundamental. Without a solution to propulsion, none of the other problems matter. Because you are not going anywhere. To understand the propulsion problem properly, you need to understand the rocket equation, derived by Konstantin Tsiolkovsky in the early 20th century. It describes the relationship between the velocity a spacecraft can achieve, the mass of its fuel, and the efficiency of its propulsion system. The critical variable is exhaust velocity, the speed at which propellant exits the engine. The higher the exhaust velocity, the more efficient the engine, and the less fuel you need for a given velocity change. But fuel has mass. That mass must be accelerated along with everything else, which means you need more fuel to move the fuel, which adds mass, which requires more fuel still. The relationship is exponential. Not linear, exponential. Doubling your target velocity does not double the fuel required. It increases it by a factor that grows rapidly, because you are carrying exponentially more fuel mass for the same payload. For chemical rockets, which power every vehicle that has ever left Earth's surface, the exhaust velocity is limited by chemistry. The energy available in molecular bonds, in the bonds between hydrogen and oxygen atoms, or carbon and hydrogen atoms, limits how fast propellant can exit the nozzle. The best chemical propellants currently available, liquid hydrogen burning with liquid oxygen, produce exhaust velocities of about 2.7 miles per second. That is the hard ceiling set by chemistry itself. Not by our engineering skill, not by budget constraints, not by the quality of our materials. By the fundamental energy available in molecular bonds, which is a fact about atoms, not about us. To reach 10% of light speed, roughly 18,600 miles per second, using chemical propulsion, you would need to carry so much fuel relative to your payload that the mass ratio exceeds anything in the observable universe. Anything. This is not an engineering problem that can be solved with larger rockets or better materials. It is a categorical impossibility with the wrong physical principle. The Saturn V was the largest, most powerful chemical rocket ever built. It sent 24 human beings to the moon. It stood 363 feet tall. At launch, it weighed 6.5 million pounds. Of that enormous total mass, nearly 6 million pounds was propellant. All of that to push a capsule containing 3 people 250,000 miles to the moon and back. Proxima Centauri is 100 million times farther away than the moon. The propellant budget does not scale linearly. It scales exponentially. By the time you account for the fuel needed to push the fuel, the required mass of propellant becomes nonsensical. Chemical rockets are not a starting point for interstellar travel that needs improvement. They are the wrong tool entirely. You need a different physical principle. Nuclear energy offers the first serious alternative. The energy released per unit mass in nuclear reactions is roughly 10 million times greater than in chemical reactions. That one factor of 10 million changes the rocket equation dramatically. Nuclear thermal rockets use a nuclear reactor to heat propellant, achieving exhaust velocities roughly 2 to 3 times higher than chemical rockets, useful for reaching planets faster, not sufficient for crossing to another solar system in any meaningful time. Nuclear pulse propulsion is more ambitious. This is Project Orion, seriously studied from the late 1950s through the mid-1960s at a facility in San Diego. Led by Ted Taylor, with significant contributions from the physicist Freeman Dyson. The concept was to repeatedly detonate small nuclear devices behind the spacecraft. Each detonation expands outward. A massive shock absorber plate at the rear of the ship intercepts the blast. The plate compresses, absorbs the energy, and springs back, transmitting an impulse to the spacecraft body. Repeat thousands of times. Build up velocity to a few percent of light speed. Freeman Dyson calculated that a large Orion spacecraft could reach Alpha Centauri in about 130 years. The physics are sound. The Partial Test Ban Treaty of 1963 ended serious development. It banned nuclear weapons, tests in the atmosphere, in space, and underwater. Orion required nuclear detonations in space. The treaty made the program politically impossible. Orion was not killed by physics. It was killed by the political reality of launching nuclear weapons repeatedly into space above populated areas. Whether a future version of this concept could be revived, perhaps with smaller devices detonated further from Earth, remains an open question. The physics has not changed. The political environment has. Fusion propulsion is the next step up. Fusion is what powers the sun. The combination of light atomic nuclei, typically deuterium and tritium, heavy forms of hydrogen into heavier nuclei, releasing the energy that binds them. The energy yield per unit mass from fusion is about 4 times greater than from fission, and roughly 10 million times greater than from chemistry. If you could build a rocket engine that used sustained fusion reactions, you could achieve exhaust velocities that make interstellar crossings in decades plausible. The problem is that we have not yet built a working fusion reactor, even for stationary power generation. The challenge is confinement. Fusion requires temperatures of hundreds of millions of degrees. Conditions hot enough that any known material would instantly vaporize. You have to contain the plasma using magnetic fields, or compress it so rapidly that it fuses before it can escape. We have achieved fusion reactions in laboratories for decades. The difficulty is achieving more energy output than input. The National Ignition Facility at Lawrence Livermore National Laboratory achieved ignition more energy out than the laser energy delivered to the target for the first time in December of 2022. A landmark result. Not a power source yet, not a rocket engine, a proof of concept that net energy fusion is possible. The ITER tokamak in France is the largest international fusion experiment ever built. A collaboration of 35 nations. It is designed to demonstrate sustained plasma operation, producing 10 times more energy than it consumes. Its construction has taken decades. The distance between ITER and a fusion rocket capable of an interstellar mission is still enormous. We are not there. Optimistic projections put useful fusion propulsion for interstellar missions sometime in the 22nd century. Conservative projections stretch further. Either way, not soon. Antimatter propulsion represents the theoretical maximum. When matter and antimatter meet, both annihilate completely. Every bit of mass converts directly into energy, according to E equals mc squared. No other reaction comes close to this efficiency. Chemical combustion converts roughly 100 millionth of 1% of mass into energy. Fission converts a little over 1/10 of 1%. Fusion converts a little over half of 1%. Antimatter annihilation converts 100%. If you could run an engine on matter, antimatter, annihilation, you could, in principle, accelerate a spacecraft to a substantial fraction of light speed with relatively modest amounts of fuel. The problem is that antimatter does not exist naturally in useful quantities. The reason goes back to the Big Bang. The early universe produced matter and antimatter in nearly equal amounts. But slightly more matter was produced, roughly 1 extra matter particle for every billion matter-antimatter pairs. The matter and antimatter annihilated each other. The slight excess of matter survived and became everything you have ever seen or touched. Every atom of antimatter now has to be manufactured. We manufacture it using particle accelerators, smashing particles together at high energy. Occasionally, the collision produces an antiproton or a positron that can be captured and stored. The production rate across all particle accelerators on Earth combined is measured in nanograms per year, billionths of a gram. To fuel an interstellar mission, you would need kilograms. The ratio between what we currently produce and what we would need is at minimum 1,000,000,000,000 to 1, and almost certainly far more when the scale of an actual interstellar fuel load is considered. This is not a gap that is bridged by building more accelerators. It is a gap that requires a completely different production pathway, one that does not currently exist even in concept. And if you somehow had the antimatter, storing it requires perfect magnetic containment for the entire mission duration. Antimatter cannot touch normal matter. If the containment fails at any point, you have an uncontrolled annihilation event. Antimatter propulsion is the most energy-dense option physics permits, and it is not accessible to us in any engineering sense on any foreseeable timeline. Laser-driven light sails offer the most credible near-term pathway to reaching another solar system with a probe. The concept: a tiny spacecraft attached to a thin reflective sail pushed by focused laser light. Radiation pressure. The force light exerts on surfaces it hits accelerates the sail. No propellant required on the spacecraft itself. All the energy comes from the laser installation, which stays at home. The Breakthrough Starshot initiative was announced in 2016, funded by the investor Yuri Milner, with a scientific advisory board including some of the leading names in astrophysics. The goal: send probes to Alpha Centauri at 20% of light speed. At 20% of light speed, the crossing takes about 20 years. 20 years, not 75,000. The physics are real. Radiation pressure has been demonstrated and measured. Solar sails have been tested in space. The idea is not speculative in principle. The engineering challenges are severe. The spacecraft would weigh about 1 gram total. The sail, a few meters across, made from material thinner than the thinnest film we currently know how to fabricate at scale. The instrument package, smaller than your thumbnail. Capable of capturing images and transmitting them home across 4 light-years of space. The laser array would need to deliver gigawatts of power, focused precisely on an accelerating target over a period of minutes. As the sail speeds away, maintaining beam coherence across thousands of individual laser units requires coordination beyond anything we have attempted. The sail material must reflect the laser light with near-perfect efficiency. Any absorbed energy becomes heat. Heat destroys the sail during the acceleration phase before it has gone anywhere. And once the sail is up to speed, it cannot stop. There is no braking mechanism, no way to slow down. The laser is behind you and receding. At the destination, the probe would fly through the Alpha Centauri system at 20% of light speed. A few hours of observation time, transmit whatever data it gathered, and continue into deeper space. 4 years after that, the signal would arrive at Earth. 24 years, minimum, from launch to first data. The technology does not yet exist in the form required. Breakthrough Starshot is a research program working toward it. The sail material is not ready. The laser array is not built. The miniaturized instruments are not at the required capability. But unlike antimatter drives or wormholes, there is no obvious physics barrier that makes it impossible. It is an engineering challenge, not a fundamental limit. What it would deliver at the destination is a gram. A brilliant, extraordinary gram of human engineering. But still, a gram. No human, no large payload, no ability to slow down and look around. And even this, the most credible approach available, is likely decades from readiness. There is one dimension of crossing the gap that most discussions underemphasize: the communication problem. Radio signals travel at the speed of light. Information cannot travel faster. This is not a technology limitation. It is a property of the universe. If a crewed mission made the crossing to Proxima Centauri at 10% of light speed, taking 42 years, communication with Earth would degrade in a specific and relentless way throughout the mission. At launch, the spacecraft is near Earth. Delay is negligible. 1 year into the mission, the spacecraft is about 0.1 light-years from Earth. Messages take about 36 days each way. A round-trip exchange takes over 2 months. Slow, but functional. People have waited longer for letters. 5 years in, 0.5 light-years out, about 6 months each way. A year for a round-trip reply. 10 years in, 1 light-year out, 1 year each way, 2-year round trip. By now, the crew is effectively making all operational decisions without any possibility of consulting Earth in real time. Any crisis must be resolved before Earth even knows it happened. Medical emergency, equipment, failure, navigation, deviation. Whatever comes up, you are on your own. 21 years in, halfway through the crossing, roughly 2 light-years from Earth. 4-year round-trip communication time. The crew sends a message describing what they have observed, what questions they have. By the time the reply arrives, 4 years have passed. The situation the reply addresses is 4 years old. The crew has adapted, changed course, moved on. The reply may be entirely irrelevant to current circumstances. At arrival, 4 light-years from Earth. Messages take 4 years each way. 8.48 years, round trip. A conversation of 5 exchanges would take over 40 years. The people who launched the mission would be old or dead before the ship arrived. The institutions that funded it might have changed beyond recognition. The political context that made it possible might no longer exist. And the crew would know this, feel it accumulating every year, as the delay grew and the connection to home thinned. Not just physically isolated, temporally isolated. The farthest from Earth any human has traveled is the Moon. About 1.3 light seconds, 2.6 seconds, round-trip communication delay. The Apollo astronauts found it slightly awkward in conversation, a beat before each reply, nothing dramatic. Now, multiply that by a factor of roughly 100 million, from 2.6 seconds to 4 years. The psychological reality of that isolation has no parallel in human experience. It is not something you can train for, because there is nowhere on Earth where you can experience communication delays measured in years. You would be, in every practical sense, alone, across a distance that makes loneliness into a physical fact of the universe rather than a feeling. Consider the architecture of our stellar neighborhood. Within 5 light-years of the Sun, 1 stellar system, Alpha Centauri, our closest neighbor. Within 6 light-years, 2 stellar systems. Within 8 light-years, 4 stellar systems. Within 10 light-years, about 7 stellar systems, roughly 12 individual stars. Within 20 light-years, about 40 stellar systems. This is the density of our galactic neighborhood, not unusual, not sparse, average for our position in the Milky Way. The average separation between stars in this region of the galaxy is roughly 4 to 5 light-years. Every one of those nearby systems is separated from us by a gulf that, at our fastest current speed, takes tens of thousands of years to cross. And separated from each other by similar gulfs. Now, consider who those neighbors actually are. Alpha Centauri is a triple system. The main pair sits 4.37 light-years away. Alpha Centauri A and Alpha Centauri B are two stars broadly similar to our Sun. Sun-like in mass, in temperature, in luminosity. They orbit each other with a period of about 80 years. At their closest, about 11 times the Earth-Sun distance. At their widest, about 36 times. That pairing is interesting. Planets could orbit either one. But the gravitational interaction between two stars can destabilize planetary orbits, particularly at distances where liquid water might exist. Whether the system has Earth-like planets in comfortable orbits is uncertain and actively studied. Proxima Centauri is the third member of the system and the closest individual star to us. A small, red dwarf, orbiting the Alpha Centauri pair at an enormous distance, perhaps 15,000 times the Earth-Sun distance, taking roughly 500,000 years to complete one orbit. Proxima has a confirmed planet, Proxima b, discovered in 2016. It orbits in the zone where liquid water could in principle exist on the surface. But Proxima is an active flare star. It regularly produces intense ultraviolet and X-ray flares, sudden, explosive releases of energy from its surface. At the distances where Proxima b orbits, those flares would periodically expose the planet to radiation intensities, far beyond what Earth's surface ever experiences from our Sun. Over billions of years, those flares may have stripped away any significant atmosphere Proxima b once had. Without a magnetic field of sufficient strength, an atmosphere under continuous flare bombardment gets slowly eroded, molecule by molecule, into space. Whether Proxima b has retained any atmosphere, whether liquid water exists on its surface, whether anything interesting is happening there at all, genuinely unknown. The second closest stellar system is Barnard's star, 6 light-years away. A dim red dwarf, smaller than Proxima, one of the nearest stars to us, and among the least luminous visible through amateur telescopes. After decades of false alarms, 4 planets were finally confirmed there. The first in 2024, the remaining 3 in 2025. All 4 are smaller than Earth. All 4 orbit far too close to the star for liquid water. Third is the Wolf 359 system at 7.9 light-years. Wolf 359 has a luminosity about 1.5 thousandths of the Sun's. You cannot see it without a telescope, despite being one of the 5 closest individual stars to our Sun. Fourth is Lalande, 21,185 at 8.3 light-years. Red dwarf. Fifth is Sirius at 8.6 light-years. The exception among our neighbors. The brightest star in the night sky as seen from Earth. Not because it is unusually close, 8.6 light-years is not unusually close, but because it is genuinely large and luminous, about twice the mass of the Sun and 25 times more luminous. It blazes. Sirius has a companion, Sirius B, a white dwarf that once was a star much more massive than the Sun and has already burned through its fuel and collapsed. no known planets around the system. The list continues. Epsilon Eridani at 10.5 light-years. Ross 128 at 11 light-years. EZ Aquarii at 11.3 light-years. 61 Cygni at 11.4. Most of them are red dwarfs. Small, dim, cool, long-lived, and often highly active with surface flares. Red dwarfs make up about 75% of all stars in the galaxy. Our Sun, a yellow dwarf of modest size and unusual stability, is by cosmic standards a relatively large and unusually well-behaved star. The nearest solar system is not what the imagination supplies. The nearest neighborhood is dominated by dim red stars, many of them flare-prone, with uncertain planetary environments. The most sun-like star among our nearest neighbors is Alpha Centauri A, at 4.37 light-years. From most of the northern hemisphere, it never rises above the horizon. The next most sun-like is Epsilon Eridani, at 10.5. Then Tau Ceti, at 11.9 light-years. These are the targets for any future interstellar mission motivated by finding sun-like environments. And they are all, without exception, separated from us by the same type of gulf that makes our fastest current spacecraft irrelevant as a crossing mechanism. There is a concept that has captured popular attention for decades: the warp drive. The idea that space-time itself could be curved or warped in a way that effectively moves a spacecraft from one place to another faster than light would travel through ordinary space. Let's be honest about this. General relativity. Einstein's geometric theory of gravity, published in 1915, allows for curved space-time. It is one of the best-tested theories in physics. GPS satellites require relativistic corrections to function. Gravitational wave detectors confirmed predictions. The theory made 100 years before we could detect them. The mathematics of general relativity also permits, in principle, certain configurations of space-time that behave oddly, that allow apparent shortcuts between distant points, or that allow a region of space to move faster than light relative to the surroundings, even though nothing inside it exceeds light speed locally. Wormholes are one such configuration. Theoretical connections between separated regions of space-time, allowing passage between distant locations without traversing the intervening space. In the mathematics, called Einstein-Rosen bridges. They are permitted by the equations. The problem is what it would take to make one exist. Traversable wormholes, ones large enough to send anything through, stable enough not to collapse immediately, require exotic matter with negative energy density. Not just very low energy density. Negative. Matter that has negative mass energy, which means it gravitates in the opposite direction from normal matter. We have never observed anything like this. Certain quantum effects produce something that resembles negative energy in extremely tiny regions. The Casimir effect is the most cited example, a measurable attraction between two very closely spaced conducting plates due to quantum vacuum fluctuations. But the amounts involved are extraordinarily small. The amounts required to stabilize a wormhole large enough for a spacecraft would be incomprehensibly larger, and there is no known reason to think they can be scaled up. The Alcubierre metric, proposed in 1994, describes a different kind of space-time geometry. A bubble that contracts at the front and expands at the rear, carrying an enclosed flat region that moves through the universe. In principle, faster than light. The original formulation required exotic matter. Research, published in 2024, described a warp drive solution using only positive energy matter. No exotic material required. This was genuinely interesting to physicists. It represented real mathematical progress in understanding what space-time geometries are possible. But the design is subluminal. It moves slower than light. It does not solve the interstellar crossing problem in the sense of making travel times short. And it remains a set of equations, not an engineering blueprint, not a testable prototype, not a technology. The honest answer is that we do not know whether shortcuts through space-time are physically realizable. The mathematics allow configurations that look like shortcuts. Whether they can be built is a different question. Whether the energy conditions can actually be met, whether quantum gravity effects at the relevant scales would prevent them, whether the universe permits them at the engineering level, even when the classical equations suggest they might work. All of that is open. There is no classified program that has solved this. There is no suppressed technology. There is genuine uncertainty about whether it is possible at all. And from where physics stands today, the gap between solar systems looks like it has to be crossed the hard way. Through the void, over real time, if it is crossed at all. Think about what the gap between solar systems means for the question of whether we are alone. The universe is about 13.8 billion years old. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. A significant fraction of those stars have planets. Multiple independent detection methods have now confirmed thousands of planets around other stars. Statistical analysis of the data suggests essentially every star has at least one planet. The galaxy is not mostly starlight and void. It is starlight and planets, a vast diversity of worlds orbiting nearly every point of light in the sky. Roughly 1 in 5 sun-like stars appears to have an Earth-sized planet in the habitable zone, the range of orbital distances where liquid water could exist on the surface. If that fraction applies across the galaxy, the Milky Way may contain something like 20 billion potentially Earth-like planets. And the Milky Way is one of at least 2 trillion galaxies in the observable universe. These numbers suggest that life, if it arises with any regularity at all, should have arisen many times, across billions of years of cosmic history, across a nearly incomprehensible number of worlds. And yet, we hear nothing. No signals, no megastructures, no engineering on a galactic scale, no replies to our transmissions. No detected patterns in the electromagnetic spectrum that suggest intelligence behind them. The universe appears quiet. This is the Fermi paradox. Named for the physicist Enrico Fermi, who raised it in a casual lunchtime conversation in 1950 with the simple observation: if intelligent life is common, where is everybody? There are many proposed answers. Life might be rare. Complex life might be rarer still. The emergence of intelligence might require an improbable sequence of events that has occurred only once or a handful of times. Or civilizations might tend to destroy themselves before reaching a stage where they can communicate across interstellar distances. Or communication is happening and we are not recognizing it. Or the universe is younger than it looks to life. All of these are serious. But the gap between solar systems is one of the most compelling answers on this list, and it receives less attention than it deserves. The distances may simply be too large for civilizations to spread rapidly across the galaxy, or even to maintain contact across it. Even a species that survived for millions of years might expand into the nearest few dozen stellar systems through extraordinary effort, and then confront the next layer of gaps. The energy costs compound. The generational timescales stretch. The communication delays grow to years per exchange. Populations separated for centuries diverge biologically and socially. Further expansion becomes exponentially harder with each layer. Every civilization, wherever it sits in the galaxy, faces the same physics. Light years of space in every direction. Neighbors separated by distances that require decades to cross, even with technology that does not yet exist. Effective isolation enforced, not by physics preventing communication, but by physics making it slow enough to be practically useless for coordinated expansion. A galaxy potentially full of intelligence. But each island of intelligence, separated from the others by gaps that make meaningful connection extraordinarily difficult. This might be the normal condition of intelligent life in the universe. Not extinction, not rarity, but isolation, enforced by the gap between solar systems, preventing any civilization from becoming a genuinely galactic presence on any reasonable timescale. The silence of the universe may not mean the universe is empty. It may mean the universe is full and very, very spread out. Stars are abundant. The universe has been extraordinarily generous with stars. What it has not been generous with is proximity. The Milky Way contains somewhere between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. The average separation between stars in our part of the galaxy is around 4 to 5 light-years. This is not a sparse region or a dense one. It is typical. Every solar system in this part of the galaxy faces the same architecture, roughly 25 trillion miles of space in most directions before reaching the next star. And those stars themselves face the same gap in their own directions. The galaxy is not a city with districts connected by roads. It is an ocean, with islands scattered across it, each island separated from the next by a crossing that takes our current technology tens of thousands of years. Even at speeds that do not yet exist, 10% of light speed crossing from one star to the next takes decades. And after that crossing, another gap of similar scale lies between you and the next island. And another after that. If you could travel at 10% of light speed and visit each of the 400 billion stars in the Milky Way in sequence, spending no time at any of them, the total journey would take over 4 trillion years. The universe is 13.8 billion years old. A journey across the Milky Way at a speed that does not yet exist would take 300 times the current age of the universe. This is the architecture of the galaxy we were born into. It is not a city. It is an ocean of unfathomable size, with islands scattered too widely for any traveler to visit more than a few in a lifetime, in a civilization's entire span of existence. The gaps repeat, gap after gap after gap, across 400 billion stars, in one galaxy among 2 trillion. This is what the distance between solar systems means at the largest scale. The most immediate implication, the one that gets mentioned least in popular discussions of space and interstellar travel, is that Earth is irreplaceable on any timescale relevant to our civilization. There is no nearby refuge. There is no second home we can reach in years or decades with current or near-future technology. The gap between solar systems is large enough that if something went catastrophically wrong on this planet, the physics of interstellar space offer no rescue on any meaningful timeline. Mars is reachable. It has been visited by rovers and probes. Human missions to Mars are plausible within this century. But Mars is barren, cold, radiation-bathed. No meaningful atmosphere, no liquid water on its surface, no biosphere. It is an engineering project of staggering complexity to make it survivable. It is not a refuge in the sense that preserves what makes Earth valuable. The moons of Jupiter and Saturn Europa, Enceladus may contain liquid water oceans beneath their ice surfaces. Life may exist there, but they are even less hospitable as places for human civilization than Mars. The nearest solar system with any candidate habitable worlds is 4 light-years away. That is the hard limit. On any honest assessment, the evidence from astronomy says this particular planet is not easily replaced. With its magnetic field, its thick nitrogen-oxygen atmosphere, its surface temperature stabilized by ocean circulation, its abundant liquid water, its active plate tectonics, its protective ozone layer, the biological complexity that evolved over 4 billion years. Not by any means we have, not from anywhere we can reach, not on any timeline that human institutions can meaningfully plan for. The gap between solar systems is not just a fact about astronomy. It is a fact about value. It says, this is the only one you've got. The picture of our stellar neighborhood that has emerged from decades of exoplanet discovery is worth understanding carefully, because it changes how we think about what we are actually looking at when we look at the night sky. We have confirmed the existence of thousands of planets around other stars. We have detected them using multiple independent methods, and the results from different methods agree with each other, providing high confidence. The transit method watches for the dimming of a star as a planet crosses in front of it. If the planet is exactly aligned with our line of sight to the star, it blocks a small fraction of the starlight at regular intervals, creating a characteristic pattern. The radial velocity method detects the tiny wobble a planet induces in its star. As the planet orbits, the star also moves in a small corresponding orbit around their common center of mass. This motion causes the star's light to shift slightly toward blue when the star moves toward us, slightly toward red when it moves away. Measuring this shift with extreme precision reveals the planet. The direct imaging method actually photographs large planets around relatively nearby stars. This requires masking the star's overwhelming brightness and isolating the much fainter reflected light from the planet. Each method has different sensitivities and biases. Transit detects planets with orbits aligned to our line of sight. Radial velocity detects massive planets in close orbits most readily. Direct imaging detects large planets far from their star. Used together, they provide a comprehensive picture, and the picture is clear. Planets are ordinary. Every star we have examined carefully has planets, or at least evidence consistent with having them. The solar system is not unusual. The presence of planets around a star is the expected state, not the exception. Some of those planets orbit in the habitable zones of their stars. Some have conditions that might support liquid water. Some have atmospheres. The James Webb Space Telescope, launched in December of 2021, can analyze the atmospheres of some of these worlds using transmission spectroscopy. When a planet transits its star, some of the starlight filters through its atmosphere on the way to our detectors. Different molecules absorb different wavelengths. By analyzing which wavelengths are diminished, we can determine which gases are present. We have detected carbon dioxide in exoplanet atmospheres. We have detected water vapor signatures. We are building toward detecting the combinations of molecules that would be difficult to explain without biological activity. Oxygen, methane, and nitrous oxide in combination, for example. A mix that chemistry alone tends not to sustain. Biological processes are required to keep producing it against reactions that would otherwise destroy it. We have not detected this combination yet in any exoplanet atmosphere. But we are looking. The TRAPPIST-1 system is the most famous target. 7 planets orbiting a small red dwarf about 40 light-years from Earth. At least 3 of those planets orbit in or near the habitable zone. The system has been studied intensively by every major telescope available since its full structure was announced in 2017. 40 light-years away. At 10% of light speed. 400 years of travel. The gap between solar systems does not just constrain our ability to travel. It constrains our ability to follow up on the most interesting things we find. We can detect molecules in the atmosphere of a planet 40 light-years away. We are developing the capability to do this with increasing precision. Within decades, we may be able to say with confidence whether a planet in the habitable zone of a nearby star has biosignatures in its atmosphere. And then we would know. We would know something lives there. And we could not go. Not with anything close to what we currently have or can see on the horizon. We would be in the position of watching something extraordinary from an uncrossable distance with no means of closing it. That is the knowledge the gap between solar systems leaves us with. The universe is full of worlds, and the worlds are far. There is one more thing worth saying about how we came to understand this distance. Because the gap between solar systems was not always known. For most of human history, no one knew how far the stars were. People knew the stars were distant. They could see that the moon was nearer than the stars, that the planets were somewhere between, that the stars formed the background against which everything else moved. But the actual distances were unknown. The measurement required a concept called parallax. Stand in one position and look at a nearby object against a distant background. Then move a known distance and look again. The nearby object appears to have shifted against the background. The amount of shift, combined with the distance you moved, tells you how far away the object is. Surveyors use this method on Earth. Hold your thumb in front of your face. Close one eye, then the other. Your thumb appears to jump relative to the wall behind it. This is parallax. Your 2 eyes are separated by a few inches, and that separation is enough to create a detectable shift. To measure stellar parallax, astronomers use a much larger baseline, the orbit of Earth around the Sun. In January, Earth is on one side of the Sun. In July, Earth is on the opposite side. The distance between these 2 positions is about 186 million miles, the diameter of Earth's orbit. Using this baseline, astronomers can measure the apparent shift of a nearby star against the background of much more distant stars over the course of a year. The technique works, but the shifts are tiny. For even the nearest stars, the parallax angle is less than 1 arcsecond. An arcsecond is 1/3600th of a degree. The full moon spans about 1800 arcseconds. Stellar parallax for the nearest stars is smaller than that. Thomas Henderson was a Scottish astronomer stationed at the Royal Observatory at the Cape of Good Hope in South Africa. In the early 1830s, he made the first accurate measurement of stellar parallax, targeting Alpha Centauri. He measured a parallax angle of roughly 1 arcsecond, indicating the system was about 4 light-years away. He delayed publishing because he was uncertain of his measurements. He feared making a claim that would later prove wrong. Friedrich Wilhelm Bessel, a German astronomer, published his parallax measurement of the star 61 Cygni in 1838. Just before Henderson published his Alpha Centauri result, Bessel got credit for the first published stellar parallax measurement. But Henderson had the closer star. What those measurements established, for the first time in human history, was the actual scale of the gap between solar systems. Not an estimate, not a guess, not a mythological or philosophical speculation about the distance to the stars. An actual number, derived from observation, from geometry, from careful repetition, from the baseline of Earth's orbit. The nearest stars were found to be several light-years away. Multiple years of light travel to the nearest one. That result was published in 1838. It came more than 200 years after Galileo first pointed a telescope at the sky. It took that long to answer the most basic question about our cosmic neighborhood. How far is the nearest star? Now we know it to within a fraction of a percent. 4.24 light-years to Proxima Centauri. And the knowing of it does not make the distance shorter. It just makes our situation clearer. The deceleration problem deserves its own discussion, because it is something most popular accounts of interstellar travel skip over. Getting a spacecraft up to a significant fraction of light speed is one challenge. Getting it to slow down at the destination is an entirely different one. And in many ways, it is harder. When you are accelerating away from the solar system, you can push against the sun's gravity. You can use a gravity assist from the planets, swinging around Jupiter or Saturn to borrow momentum from their orbital motion. You can power your engines for years, gradually building up velocity. At the destination, none of that is available. You arrive moving at 10% of light speed, roughly 18,600 miles per second, and you need to slow down. If you do not slow down, you fly through the system in hours, a brief and unrepeatable passage, like breakthrough starshot. No orbit insertion, no landing, no extended study, just a flash through and then gone. To stop, you need to decelerate, and deceleration requires the same energy as acceleration, which means you need to carry enough fuel not just to get up to speed, but to slow down at the end. This roughly doubles the fuel requirement on top of what the rocket equation already demands. Some proposals get around this by using the destination star's light pressure to brake the spacecraft as it approaches. A light sail on the way in, using the star's radiation as a braking force. This works, in principle. The force is small, but over a long approach, it can be cumulative. The problem is that it requires an enormous sail, and the approach trajectory has to be precisely tuned to maximize the braking time. A slight miscalculation, and you pass through too fast. Another proposal involves the Bussard ramjet, conceived by physicist Robert Bussard in 1960. The idea: scoop up the hydrogen in the interstellar medium using a magnetic funnel, fuse it in an onboard reactor, use the fusion energy to drive the spacecraft forward. In principle, you would never run out of fuel. You are continuously gathering it from the medium around you. The concept is elegant. The problems are severe. The density of hydrogen in interstellar space is so low that the magnetic scoop would have to be hundreds of miles across to gather enough hydrogen to sustain fusion at useful rates. The energy required to generate and maintain such a scoop may exceed the energy generated by the fusion. The drag from scooping the interstellar medium may actually slow the spacecraft as much as the thrust propels it forward. Subsequent analysis has generally found that the Bussard ramjet does not work in the original formulation. But it remains a starting point for thinking about designs that harvest fuel from the medium rather than carrying it all. The deceleration problem is not a footnote. It is half of the total propulsion challenge, and it is frequently unaddressed in casual discussions of interstellar travel. A crewed mission that can accelerate to 10% of light speed but cannot decelerate at the destination is not a mission. It is a very expensive way to give a crew an extraordinarily brief view of another solar system before they continue into the void. Then there is the problem of what happens inside a spacecraft crossing the gap at speed. Not to the systems, to the people. Human beings evolved on Earth. Our biology is calibrated to Earth's gravity, its atmospheric pressure, its magnetic field, its radiation environment, its day-night cycle, the presence of other humans, the sensory richness of a living planet. Remove any one of those things, and problems begin. Remove all of them simultaneously, for decades, and you are in territory that biology has never faced before. Muscle and bone degrade in microgravity. Without the constant mechanical loading that gravity imposes, the body begins to dismantle structures it judges unnecessary. Bone density drops at roughly 1 to 2% per month without countermeasures. Muscle mass follows. Cardiovascular efficiency changes as the heart adapts to a body no longer pulled downward. Astronauts on the International Space Station, on missions of 6 months to a year, require months of rehabilitation after returning to Earth's gravity. The effects are well documented, and the countermeasures vigorous exercise for 2 hours per day only partially work. An interstellar crossing at 10% of light speed takes 42 years. Gravity could be simulated through rotation. A spacecraft spun at the right rate produces centrifugal force that mimics gravity along the outer rim. This is not a new idea. It appears in science fiction because it follows directly from physics and engineering. But a rotating habitat adds structural complexity and mass, and requires careful design to avoid motion sickness effects that come with certain combinations of rotation rate and habitat radius. Then there is vision. Astronauts, returning from long missions, frequently report changes in visual acuity associated with a condition called spaceflight-associated neuroocular syndrome. Fluid redistribution in microgravity appears to alter the pressure dynamics around the optic nerve and the shape of the eye. Some astronauts have experienced lasting vision changes. We have documented this over the timescales of the longest space missions to date. The record single continuous stay in orbit is just over 437 days, set by cosmonaut Valery Polyakov aboard the Mir space station in the mid-1990s. We do not know what 42 years of spaceflight does to a human body. We cannot know. No human has been in space for 42 years. No human has spent decades in a radiation environment like interstellar space. The data does not exist because the experience does not exist. The human body in deep space for decades is genuinely unexplored territory. And the biology is not the only dimension. The psychology matters too. Humans are profoundly social animals. Our brains evolved in environments where we were embedded in groups, tracking relationships, responding to social cues, navigating hierarchies. Isolation from all of that is not a minor inconvenience. It is a fundamental challenge to the kind of minds we have. Isolation studies on Earth, Antarctic winter overcruise, submarine deployments, isolated habitats consistently show that small groups, isolated for long periods, develop characteristic psychological patterns. Interpersonal conflict increases. Motivation varies. People find ways to cope that are not always healthy. Some manage extremely well. Some struggle. The longest Antarctic winter over missions last about a year. Interstellar missions last decades. And there is one psychological dimension of interstellar travel that has no parallel in any Earth-based isolation study: the communication delay. On every Earth isolation study, on every Antarctic mission, on every submarine deployment, the isolated person or group can reach home. They can call. They can receive messages from family, from friends, from the world. Even the Antarctic crews email daily with anyone they want. On an interstellar mission, this option vanishes. It does not get difficult. It does not get slow. It disappears. After 10 years into the crossing, a message home takes a year to arrive, and the reply takes a year to return. You can send your children's birthday messages and have them arrive in time. Barely. After 20 years, you are sending messages that arrive 2 years after the event they reference. Your parents are aging. They are getting older by the time your words reach them. By the time a reply returns, 4 years have passed. They might not be alive anymore. After 30 years, you are in a space so isolated that the light from our sun is dimming in your sky. Earth is a faint blue-green point in a sea of stars. Every message home is a message into the past, to a civilization that has been living and changing for decades in a reality you cannot follow. This is not just hard. It is a kind of loss without precedent. The experience of watching everything familiar recede beyond meaningful contact, while still being alive, still caring, still human. How the psychology of that manifests over decades. Whether people adapt, find new anchors, build a complete new world within the ship, or whether the isolation compounds into something that jeopardizes the mission, is unknown. It may be the hardest problem in interstellar travel, not because it is unsolvable, but because we do not know how to solve it. Navigation through interstellar space has a subtlety that most discussions overlook. You are not navigating through a fixed backdrop. Everything is moving. The Sun orbits the center of the Milky Way at about 500,000 miles per hour. Alpha Centauri has its own orbital velocity. It is moving relative to us. The component of its motion, directed toward or away from us, the radial velocity, is currently about minus 13.9 miles per second, negative meaning toward us. The system is approaching. By the time a spacecraft launched today reached the current position of Alpha Centauri, decades or centuries, depending on the technology, Alpha Centauri would no longer be at that position. You aim not at where the star is. You aim at where it will be when you arrive. For a 42-year crossing at 10% of light speed, Alpha Centauri will have moved considerably from its current position. Not dramatically relative to the total distance, but enough that a navigation system calibrated only to present positions would miss. You calculate the interstellar trajectory, accounting for the proper motion of the target star, the radial velocity, the gravitational effects of all massive objects along the path that might curve your trajectory, the motion of the sun itself, the effects of the interstellar medium, a navigation error of 1 arc second at launch, 1/3600th of a degree, compounds over 4 light-years into a displacement of millions of miles. Fine-tuning the trajectory requires propulsion reserves, course corrections, fuel burned during cruise phase that was intended for deceleration. Every navigation correction has a cost, and you are navigating through a medium you cannot see ahead of. The interstellar medium is not uniform. There are denser clumps of gas and dust, interstellar clouds, and more diffuse regions. There are magnetic field variations that can affect charged particles and, in principle, a spacecraft's orientation. From Earth, we can map the broad structure of the interstellar medium in our region using radio telescopes and spectroscopy. But the fine structure along a specific corridor to Alpha Centauri cannot be mapped in advance with the detail a 50-year crossing would require. A crew or an automated navigation system would have to respond to conditions encountered along the way, adjusting trajectory in real time, making decisions with latency, burning precious fuel reserves. Navigation across the gap between solar systems is not the same as navigation between planets. It is navigation through an environment never mapped over timescales no mission has ever experienced, with no possibility of calling for help. There is something else between the stars that most people do not think about: rogue planets. Planets that have been ejected from their home solar systems by gravitational interactions with other planets or with passing stars. These objects wander through interstellar space, not orbiting any star, dark, massive, completely invisible until a spacecraft was very close to one. We have detected rogue planets through gravitational microlensing, the bending of light from background stars when a massive object passes in front of them. The data suggests rogue planets may be common. Some estimates suggest there are more rogue planets in the galaxy than there are stars. Most are small, and in the vast expanse of the interstellar medium, the probability of any given spacecraft encountering one is low. But for a mission that takes 40 years, crossing 25 trillion miles of space, the probability is not zero. A rogue planet the size of Jupiter, with no starlight illuminating it, is essentially invisible to any current detection method until it is close enough to be a problem. The gravitational effect would be detectable at considerable distance. The planet would cause a slight deflection in the spacecraft trajectory, but distinguishing that deflection from other small forces requires precise measurement. This is not a dominant concern in thinking about interstellar mission hazards. The cross-sectional area of a spacecraft compared to the volume of the interstellar medium is so small that encounters with anything of significant size are rare by probability. But rogue planets are a reminder that the space between solar systems is not the empty stage it appears to be. It has inhabitants, cold, dark, massive, ancient objects that were once part of solar systems like ours and were thrown out into the dark. Some of them may retain subsurface oceans, kept liquid by internal radioactive heating or pressure, long after any starlight that once warmed them is a distant memory. The interstellar medium has a geology, a population of wandering worlds, a history visible only to something close enough to see it. Between us and Proxima Centauri, in that 25 trillion miles of space, there may be one of these objects, several, potentially. We would never know it unless we crossed the gap. Another dimension of the gap between solar systems that tends to be underappreciated is what it does to time. Not just travel time, relativistic time. At speeds approaching a significant fraction of light speed, time does not pass the same way for the traveler as it does for the observer left behind. This is time dilation, one of the confirmed predictions of special relativity. At 10% of light speed, the time dilation effect is small but present. A traveler at that speed ages slightly slower than someone stationary relative to them. The factor is roughly 0.5%. Over 42 years of travel, the crew would experience about 42 years, minus roughly 2.5 months, compared to Earth time. Not dramatic at 10%. At 50% of light speed, the difference grows. The traveler experiences about 87% of the time that passes on Earth. A crossing to Proxima that takes 8.5 years as measured by Earth would feel like about 7.25 years to the crew. At 90% of light speed, the crew experiences about 44% of Earth time. The crossing feels like about 2 years. At 99% of light speed, the crew experiences about 14% of Earth time. A few months of subjective experience for a journey that takes over 4 years from Earth's perspective. In principle, at speeds very close to light speed, a crew could cross the galaxy in a subjective human lifetime. The problem is the energy required. Getting to 90% of light speed requires a mass ratio so extreme that it makes the already impossible mass ratios for 10% look modest. Getting to 99% requires even more. Getting to 99.9% approaches mass ratios that are physically meaningless. You would need more energy than is available in any practical fuel source. Time dilation is a real effect. It does not solve the interstellar travel problem. It is not a trick that makes the gap between solar systems navigable. It is a feature of physics that might, at extreme velocities, humanity has no means of achieving, compress the subjective experience of the crossing. But those velocities are beyond any propulsion concept that has a realistic engineering pathway. For the speeds that are actually conceivable, 10 or 20% of light speed, time dilation is a minor footnote. 42 years is roughly 42 years, give or take a couple of months, for both the crew and the planet they left behind. Project Daedalus is worth understanding in some detail because it represents one of the most serious and complete engineering studies ever conducted of an unmanned interstellar probe. It was conceived and designed in the 1970s by a team assembled by the British Interplanetary Society, one of the oldest and most distinguished spaceflight advocacy organizations in the world. The mission target was Barnard's Star, 6 light-years away. The design: a 2-stage fusion-powered spacecraft burning deuterium and helium-3 in fusion reactions to generate thrust. The reason for 2 stages is the rocket equation. A single stage, carrying enough fuel to reach 12% of light speed, would be dominated almost entirely by fuel mass. Staging allows the empty first stage to be discarded once its fuel is spent. That dramatically improves the mass fraction of the second stage. The vehicle's total mass was calculated at roughly 54,000 metric tons. Most of that mass, approximately 50,000 metric tons, was fuel for the first stage. The second stage, after first stage separation, would weigh roughly 1,000 metric tons. Its payload, the actual scientific instruments, and probe body about 500 metric tons. At 12% of light speed, the crossing to Barnard's Star takes about 50 years. No deceleration. The probe would fly through, observe, transmit, and continue into deeper space. The team calculated that around 250 pellets of deuterium-helium, 3 fuel mix would be injected into the fusion reaction chamber per second and ignited by electron beams, with each detonation generating thrust. The engineering is demanding at every level. Sustained, controlled fusion reactions, something we still cannot achieve in stationary power plants on Earth today, 50 years after Daedalus was designed. Helium-3, in the quantities required, does not exist on Earth in usable amounts. The design assumed mining it from the atmosphere of Jupiter. A mining operation in the atmosphere of Jupiter as a prerequisite step to building the interstellar probe. The final design study was published in 1978. It took 4 years to complete. It is still the most detailed publicly available blueprint for an unmanned interstellar mission using physics and engineering that is, at least in principle, grounded in known science. That study is nearly 50 years old now. We have not built it. We have not built anything like it. The technologies it depends on: controlled fusion, helium-3, mining at scale, the construction of a 54,000 metric ton spacecraft, do not exist. Daedalus was not a near-term proposal. It was a proof of concept, a demonstration that an interstellar mission could be designed using physics we understood, even if the engineering was extremely far from ready. It remains a proof of concept 50 years later. The interstellar medium between here and Proxima Centauri is not just gas and dust. It has a chemistry. In the thin hydrogen and helium that fills the space between stars, other molecules exist in trace amounts. Carbon monoxide, water, formaldehyde, hydrogen cyanide, methanol. Molecules of increasing complexity have been found in interstellar clouds throughout the galaxy. In the denser regions, the giant molecular clouds where stars form, the chemistry becomes surprisingly rich. Amino acids, the building blocks of proteins, have been detected in meteorites in forms that appear to have been synthesized in the interstellar medium before being incorporated into our solar system when it formed. Some of the organic chemistry that enabled life on Earth may have been seeded from interstellar space. The space between solar systems is not chemically inert. It is a slow, cold, radiation-bathed laboratory. Chemical reactions proceed over millions of years, driven by the ultraviolet light from distant stars, producing molecules that accumulate in dense clouds. Clouds that collapse under gravity to form new stars and planets, seeding new worlds with the molecular precursors of biology. The gap between solar systems is not just a physical obstacle. It is a chemical medium with its own history, a history that may be inseparable from the history of life itself. The most common question about interstellar travel, once people understand the scale of the problem, is, why not send a signal instead? Why build a spacecraft? Why cross the gap physically? Why not simply transmit a message at the speed of light and make contact at the speed of the universe's fastest messenger? It is a reasonable question. We have been transmitting radio signals for over 100 years. The bubble of radio noise from Earth, television, radar, military communications has expanded roughly 100 light-years from Earth in every direction. Every star within 100 light-years has, in principle, received something from us. And we have been deliberately transmitting targeted signals too. The Arecibo message was sent in 1974, aimed at the globular cluster Messier 13, 25,000 light-years away. A response, even if sent immediately upon receipt, would not arrive for 50,000 years. Radio signals travel at the speed of light. For communication with the nearest solar system at 4.24 light-years, round-trip communication takes 8.48 years. If you sent a message to Proxima Centauri tomorrow and something replied immediately, the reply would arrive in 2034 at the earliest. This is not fast, but it is incomparably faster than physically traveling there. The SETI program, the Search for Extraterrestrial Intelligence, has been listening for signals from other civilizations for over 60 years. Dedicated radio telescopes scan the sky, searching for patterns that would indicate intelligent origin. So far, nothing definitive. The wow. Signal was detected in 1977 by astronomer Jerry Eman at the Big Ear Radio Telescope in Ohio. A strong narrowband radio signal lasting 72 seconds that matched what a signal from interstellar space might look like. It has never been detected again. Its source remains unknown. Occasional candidate signals have been identified and then explained as terrestrial interference, natural astrophysical phenomena, or satellites. Nothing yet that stands up to scrutiny as an artificial signal from another civilization. This silence may mean other civilizations are not transmitting in ways we can detect. It may mean they are transmitting on frequencies or with modulations we are not listening for. It may mean the gap between solar systems is still wide enough that any civilization beyond a certain distance cannot produce a signal strong enough to be detectable with our current equipment. It may mean we are alone. We do not know. But the possibility of signals of communication across the gap faster than physical travel is real and being actively pursued. If a signal were ever detected, the gap between solar systems would suddenly take on a different character. It would still be 25 trillion miles to the nearest one. We would still not be able to go there. But we would know something was on the other side of it. And that knowledge would change everything about how the gap feels. The measurement of stellar distances is worth dwelling on, not just as history, but as a demonstration of what is possible without leaving Earth. The parallax method works best for nearby stars. The farther away something is, the smaller the shift, and eventually the angle drops below what any instrument can separate from noise. For ground-based telescopes, that limit arrived at around 1,000 light-years. For stars farther than that, astronomers use a different method. Certain types of stars, Cepheid variable stars for instance, pulsate in brightness, with periods directly related to their intrinsic luminosity. Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 20th century, discovered this relationship in 1912. She was employed as a human computer, measuring and cataloging the brightnesses of stars on photographic plates. She noticed that the brighter Cepheid variables in the small Magellanic Cloud pulsated more slowly. The period of pulsation predicted the intrinsic brightness. This was transformative. If you observe a Cepheid variable anywhere in the sky, you can measure its period of brightness variation. The period tells you how intrinsically bright it is. Compare that to how bright it appears, how much of its light actually reaches you, and the difference tells you how far away it is. Edwin Hubble used Cepheid variables in the early 1920s to prove that the Andromeda Nebula was not part of our galaxy, but an entirely separate galaxy, millions of light-years away. A revolution in our understanding of scale. We discovered the universe was not the Milky Way. The Milky Way was a single galaxy among millions, then billions, now known to be one among trillions. All of this derived from the careful measurement of blinking stars. The Hipparcos satellite, launched in 1989, measured the parallaxes of over 100,000 stars with unprecedented precision. The Gaia satellite, launched in 2013, has extended this to over 1 billion stars, mapping the three-dimensional structure of our galaxy with a precision that would have been unimaginable to Henderson and Bessel. We know where the stars are. We know their distances to extraordinary precision. We know the gap between solar systems to decimal places. And still, knowing the distance changes nothing about crossing it. The measure is perfect. The crossing remains undone. There is a version of the Fermi paradox that lands differently once you understand the distances. The question is not just, Where is everyone? The question is, could anyone reach us, given the physics? Consider a civilization that arose 1 billion years ago. Life on Earth is about 3.8 billion years old. Intelligence, by any reasonable measure, has existed for at most 1 million years. A civilization 1 billion years old would have had 1 billion years to develop technology. If such a civilization solved the propulsion problem, if they found a way to cross the gap between solar systems at, say, 10% of light speed, they could, in principle, have spread across the entire galaxy. At 10% of light speed, the crossing from one star to the next takes decades. The Milky Way is about 100,000 light-years across. A journey from one side to the other takes 1 million years. 1 billion years is 1,000 times longer than that. A civilization that survived 1 billion years and spread continuously at 10% of light speed could have crossed the galaxy 1,000 times over. And yet, we see no signs of it. The galaxy does not appear to be colonized. There are no obvious megastructures. No Dyson spheres, shells of material around stars designed to capture all their energy output. No obvious engineering at the galactic scale. No signals that clearly indicate ancient intelligence. One resolution is that space simply does not permit such rapid expansion, even at 10% of light speed. The cost of each crossing is enormous, not just in propulsion, in social cohesion, in information, in the maintenance of any coherent project across the time it takes for the crossing to complete. A colony ship takes 100 years to reach the next star. In 100 years, the civilization that launched it has changed. Political support has shifted. The original motivation may no longer exist. The colony ship arrives with people who share the values of a century ago, at a destination where they are completely alone, separated by 100 light-years from anyone who cares. They have to build a new civilization from scratch. That new civilization develops its own culture, its own priorities, its own reasons to exist. The original expansion mission may not survive a single generation of colonists who were born on the ship and never chose to be part of it. The gap between solar systems does not just make travel hard. It makes the sustained, organized expansion of a civilization across multiple star systems potentially impossible to maintain. Each crossing resets the social and political context. Each colony is effectively isolated. A genuinely galactic civilization might be a physical impossibility, even for a species with the technology to cross the gap. Not because the physics prevents the crossing, but because the gap prevents the connection. And a civilization without connection is not a civilization. It is a collection of isolated experiments, each starting over, each separated from the others by decades of travel and years of communication delay. This is not a reassuring thought, but it may be an accurate one. And if it is accurate for us, it was accurate for every civilization that existed before us. The silence of the universe may not be the silence of emptiness. It may be the silence of isolation. Each mind, each civilization, each species that ever looked up at the night sky and wondered. Alone, separated from all the others by the same mathematics, the same physics, the same gap between solar systems that we face today. There is one practical implication of the gap between solar systems that shapes how we think about the future of our civilization, and it is rarely stated plainly. If we wanted to establish a genuinely self-sustaining human presence in another solar system, not a probe, not a flyby, but an actual permanent colony, The minimum viable population is estimated at between 1,000 and 10,000 individuals. You need enough genetic diversity to avoid inbreeding depression over many generations. You need enough individuals that the random loss of anyone does not eliminate critical skills or knowledge. You need enough social structure to maintain functional governance, education, medicine, engineering, and food production over centuries. 1,000 to 10,000 people in a spacecraft for 42 years at minimum. More likely centuries if propulsion more modest than 10% of light speed is what becomes available first. That spacecraft needs to be not just a vehicle, it needs to be a world. Self-contained food production, agriculture, aquaculture, or synthetic food systems capable of feeding thousands of people indefinitely without resupply. Complete water recycling, atmosphere management, medical care, including surgery, obstetrics, dentistry, and oncology, because the crew will get sick and have children and develop illness over 42 years. Education through childhood and adolescence for children born on board who had no say in the mission. Recreation and culture, because human beings deprived of meaning and novelty lose their minds. Governance, for a community of thousands isolated from any external authority or appeal. The structural mass of such a vessel would be measured in millions of metric tons. The propulsion system to move millions of metric tons to 10% of light speed does not exist. The energy required is beyond anything we have produced. The engineering required to keep such a vessel functional for decades without external support has never been demonstrated at any comparable scale. This is not pessimism about the future. It is calibration about the present. The gap between solar systems is not just about the physical distance. It is about everything the crossing requires, stacked on top of each other: the propulsion, the radiation, shielding, the navigation, the deceleration, the life support, the psychology, the governance, the biology, the communication lag. Each one a significant problem on its own. All of them simultaneously, sustained for decades. That is the gap between solar systems, stated completely. And it is worse than you think. There is something that happens when you map the stellar neighborhood accurately. You notice that the distances between star systems are not random. They follow a distribution. Most neighbors are between 2 and 6 light-years away. The very closest is 4.24. But there is no star system that is 1 light-year away, or half a light-year, or a tenth. The Oort cloud of our solar system extends perhaps 1 to 2 light-years from the Sun. The Oort cloud of Alpha Centauri presumably extends perhaps 1 to 2 light-years from that star. The two clouds, if they exist in the form currently theorized, may actually be in contact. The gravitational edges of two neighboring solar systems meeting somewhere in the middle of that 4.24 light-year gap. Objects in our Oort cloud are occasionally perturbed by the gravitational effects of passing stars, including Alpha Centauri, and sent falling inward toward the Sun, becoming the long-period comets that occasionally grace our inner solar system. The comets that visit us may be messengers from the boundary region between two solar systems. In a loose physical sense, two solar systems can be said to touch at their outermost edges while their stars remain 25 trillion miles apart. We do not know much about the Oort cloud. We have never directly observed an Oort cloud object. We have inferred its existence from the orbital properties of long-period comets arriving from all directions of the sky, suggesting a spherical reservoir extending far beyond the planetary system. The New Horizons spacecraft, which flew past Pluto in 2015, is now heading outward through the Kuiper Belt. In a few decades, it may enter the inner Oort cloud. It will not reach the outer Oort cloud in any time scale relevant to human civilization. The outer Oort cloud may be, in the most literal physical sense, the frontier of our solar system. The place where our sun's gravity barely holds sway, where an object might be simultaneously loosely bound to our sun and loosely influenced by the gravity of the nearest stars. The boundary of home, 25 trillion miles from where you are sitting right now. The final thing to understand about the gap between solar systems is what it says about the nature of discovery itself. Every major expansion in the human understanding of scale has come with a corresponding expansion in humility. We once believed Earth was the center of the universe. Then, we discovered it orbited the sun. We once thought the solar system was the extent of organized structure. Then, we discovered the Milky Way. We once thought the Milky Way was the universe. Then, we discovered it was one galaxy among billions. At each step, the universe turned out to be larger than we thought. At each step, our position turned out to be less central, less special, less privileged than we had assumed. The measurement of stellar parallax in the 1830s was one of those moments. The stars were not just decorations on a nearby sphere. They were distant suns, each separated from the others, and from us, by distances that had never before been grasped. The gap between solar systems is a fact that arrived in human consciousness as a genuine shock to the assumption of navigability. We knew space was large. We did not know it was this large in this way. Now we know, and the knowing has not diminished the night sky. If anything, it has made each point of light more significant, because now we understand what that light crossed to reach us. 25 trillion miles of nearly nothing, years of travel through cold, irradiated, almost empty space. And it arrived. The light made it. The photons that hit your eye when you look at Proxima Centauri left that star 4.24 years ago. They crossed the gap. Without a spacecraft, without propulsion, without protection from radiation, without deceleration, because light is what it is. And what it is the only thing we know of that crosses the gap between solar systems without effort. Everything else, every proposal, every design, every mission concept is a human attempt to do what light does naturally: move at the speed of light, or at least some reasonable fraction of it, across a distance that humbles everything we have ever built. That is the gap between solar systems, and the distance is worse than you think. Look up at the night sky on a genuinely dark night, away from city lights, eyes adapted for 20 minutes. The Milky Way appears as a band of diffuse light, the combined glow of billions of stars, too distant and too closely packed to be resolved individually. Individual stars stand out as points, a few thousand visible to the naked eye, each one a sun, most of them orbited by planets. The distances to the ones you can see range from a few light years for the nearest to several thousand for the most distant naked-eye objects. Sirius, the brightest star, at 8.6 light-years. Arcturus, bright and orange in the northern sky, at about 37 light-years. Vega, brilliant and blue-white in summer, at about 25 light-years. Betelgeuse, the reddish supergiant in Orion, marking the hunter's shoulder at roughly 700 light-years. Deneb, at the tail of the swan in Cygnus, the most intrinsically luminous star visible to the naked eye, at roughly 2,000 light-years. Each of those points of light is a solar system. A star with its own gravitational domain, its own planets if they formed, its own billions of years of history. And each one is separated from you and from every other one by the gap, 25 trillion miles to the nearest. Much more to most of what you can see. The night sky is simultaneously the most beautiful thing you can look at and the most honest. Beautiful because of what it contains. Honest because of what it reveals about your situation. You are on one of those points of light, separated from every other one by the same kind of gulf, able to see them, able to understand them in remarkable detail, to measure their distances, their temperatures, their masses, their ages, the composition of their atmospheres from here, not able to reach them. Not in any time frame that feels like a human life, or even a human civilization with anything we currently have or can currently see how to build. The night sky does not lie about this. It shows you the stars, and the stars are far, far, in a way that the word far does not capture until you work through the numbers. There is something in this that deserves a clear look. Our species spent most of its evolutionary history moving on foot at roughly 3 miles per hour. We learned to sail at about 10 miles per hour. We put steam engines in vehicles and reached 60. We flew at hundreds. We put rockets in space and reached 38,000 miles per hour. Each of those transitions took centuries or less. The transition from 38,000 miles per hour to a meaningful fraction of light speed, the transition required to cross the gap between solar systems in a human lifetime, is a larger step than all of those combined, not a larger step in degree, in kind. Because it is not just about going faster. It is about changing the physical principle by which you move. Every vehicle that has ever carried a human being anywhere has been, fundamentally, a machine that throws mass backward to push itself forward. Chemistry, nuclear energy, whatever the source it is, mass being expelled. Mass is limited. And the rocket equation does not produce the numbers required for interstellar crossings with any realistic amount of fuel. The next step requires not just better engines. It requires a fundamentally different relationship between energy and motion. Something that either uses vastly more energy per kilogram of spacecraft, or does not require carrying fuel at all, or does something to the structure of space rather than to the spacecraft. We do not currently have this. We do not currently have a clear, validated path to it. What we have is the gap between solar systems, fully measured, fully understood, physically fully known in its implications, and the understanding that crossing it is not just an engineering challenge. It is the engineering challenge, the most important unsolved problem in the history of our species, if we intend to become something more than a single-planet civilization. The gap between solar systems is worse than you think. Not because of the number. The number is 25 trillion miles to the nearest one, and you probably knew that was large. It is worse than you think, because of what the number implies when you take it seriously all the way through. It implies that the universe distributed its matter in a pattern that makes neighboring solar systems genuinely, profoundly unreachable by anything we have built or anything we know clearly how to build. It implies that the most fundamental act of interstellar exploration, crossing from your home solar system to another one, requires technology we do not have, and timescales that challenge every assumption we carry about what a mission, a project, or a civilization can accomplish. It implies that the night sky, as magnificent as it is not an invitation to casually spread across the galaxy. It is a display of things that are very, very far away. And it implies that this particular planet, This solar system, this specific address in the Milky Way, may be the entirety of our physical domain for centuries. Possibly for as long as our civilization exists. That is a sobering thought. It is meant to be sobering, not in the spirit of despair, in the spirit of clarity. Understanding the real scale of the problem is the only productive starting point for thinking seriously about what comes next. Not because we should give up, but because the gap between solar systems is the most important obstacle we face as a species that wants to be more than a temporary presence on a single world in an ordinary corner of a medium-sized galaxy. And obstacles of that magnitude deserve to be understood in their full size before we pretend we know how to cross them. And still, in the face of all of this, something persists. Our species spent most of its evolutionary history moving by foot. We only learned controlled flight about 120 years ago. We only reached space in the 1950s. And we have already sent objects past the edge of our solar system. We have measured the distance to the nearest solar system to within a fraction of a percent. We have identified thousands of planets around other stars. We have detected the atmospheric composition of worlds orbiting stars 40 light-years away. We have watched gravitational waves ripple through the fabric of space-time, confirming a century-old prediction. We have imaged the shadow of a supermassive black hole, 6.5 billion times the mass of the Sun, 55 million light-years from Earth, using a telescope the size of the planet. We are doing these things from a single planet, orbiting an ordinary star, in an ordinary region of an ordinary galaxy, using instruments built by hands, designed by minds. There is something in that which is neither triumphant nor hopeless. It is just honest. We are the universe, organizing itself into something capable of asking where it is, curious enough to measure the answer, honest enough to face what the answer says. The next time you step outside at night and look up, try to see what you are actually seeing. Not a decorative ceiling, not a background, a map. Each point of light is a sun, probably with planets, possibly with something looking back. And between you and the nearest one, 25 trillion miles of the thinnest, coldest, most radiation-flooded emptiness the universe naturally produces. That space is real. That distance is real. And somewhere out there, around one of those points of light, there may be something that has done exactly what we have done. Measured the distances, confronted the physics, understood the gap, and is sitting, as we are, on the near side of something it does not yet know how to cross. That shared condition, spread across 25 trillion miles of interstellar space, may be the most honest thing we have in common with anything else that exists. Good night.